Picture this. It's 1971, and a beat-up 1969 Chevelle SS pulls up to a stoplight in Detroit. Next to it, a pristine Plymouth Cuda with a 446-pack, 390 horsepower of Mopar muscle. The Cuda driver smirks at the Chevelle's primer spots and mismatched body panels. When the light turns green, the Chevelle launches like it's been shot from a cannon. By the time the Cuda driver processes what happened, he's staring at taillights disappearing into the distance. The Chevelle's engine? A stock 396 making 325 horsepower, 65 horses less than the Plymouth. This wasn't luck. This was engineering. What if I told you that for 3 years, this particular Chevelle terrorized the streets of Michigan, consistently beating cars with 50, 75, even 100 more horsepower? Cars that cost twice as much. Cars that should have destroyed it on paper. The owner wasn't a professional racer. He wasn't backed by GM's performance division. He was a tool and die maker named Frank Moretti, who worked second shift at a transmission plant and spent his nights in a 2-car garage behind a house in Dearborn. What Moretti discovered would eventually force Hot Rod magazine to rewrite their testing procedures and make Chevrolet's engineers scramble to understand what a backyard mechanic had figured out that they'd missed. This is the story of how one man's obsession with airflow dynamics and gear multiplication turned a mid-range muscle car into a giant killer. How he proved that in drag racing, horsepower is just a number, but torque application is everything. And how his weird trick, as his competitors called it, was actually a masterclass in mechanical efficiency that exposed the dirty secret of the muscle car era. Most of these legendary machines were wasting 30 to 40% of their power before it ever reached the pavement. To understand what Frank Moretti accomplished, we need to travel back to 1969, the peak year of the muscle car wars. Detroit was drunk on horsepower. Compression ratios were climbing toward the limits of pump gas. Displacement was king, 427s, 428s, 440s, 454s. If it was big, it sold. The 1969 model year alone saw the release of the Copo Camaro with its all-aluminum ZL1 427, the Boss 429 Mustang, the Plymouth Roadrunner with the 446-pack, the Dodge Charger Daytona. These weren't just cars, they were street-legal race machines. Entering Chevrolet's entry in the intermediate muscle car segment was the Chevelle SS. For 1969, you could order it with 3 versions of the 396 cubic inch big block. The base L35 made 325 horsepower, the L34 produced 350, the top dog L78 cranked out 375 horsepower with solid lifters and 11.1 compression. Above that sat the rare Copo 427s and the mythical L72 427, but those were special orders. For most buyers, the 396 was the heart of the Chevelle experience. Landetraditionnel Frank Moretti bought his Marina Blue 1969 Chevelle SS 396 new from Stark Chevrolet on Michigan Avenue. L34 engine, 350 horsepower, Muncie M21 close ratio 4-speed, 3.31.1 posi-traction rear end. Total sticker price, $3,047. It was a Wednesday car, built on a Wednesday when the line workers were in rhythm, not rushing like Monday, or tired like Friday. The fit and finish were exceptional. The engine was tight. Everything worked. For 6 months, Frank drove it stock, learning its personality, feeling its strengths and weaknesses. Then he started measuring things. Here's where the story gets interesting. Frank wasn't content to bolt on headers and call it a day. He approached his Chevelle like an engineer approaches a problem. He borrowed equipment from work, flow benches, precision measuring tools, even an early computer terminal connected to GM's mainframe. He spent 3 months just studying airflow, not modifying anything, just measuring. Intake tract volumes, port velocities, exhaust scavenging rates, pressure drops across the carburetor venturi. He filled notebook after notebook with numbers, graphs, calculations. And what he discovered shocked him. The stock 396 intake manifold, The one Chevrolet's engineers had spent thousands of hours developing had a fundamental flaw. The runners were sized for peak flow at 6,500 RPM, but the hydraulic cam in the L34 signed off at 5,500 RPM. The engine was trying to breathe through ports sized for an RPM range it would never see. Worse, the transition from the carburetor to the intake plenum created turbulence that killed velocity right where you needed it most, between 2,500 and 4,000 RPM, where street racing actually happened. But the real revelation came when Frank started analyzing gear multiplication. Every magazine focused on quarter-mile times and trap speeds. But Frank realized something crucial. Street racing wasn't about terminal velocity. It was about the area under the acceleration curve from 0 to 80 miles per hour. That's where races were won and lost. After 80, you were already breaking every speed law in America. The race was effectively over. And the math was beautiful in its simplicity. Torque at the wheels equals engine torque times gear ratio times final drive ratio minus losses. Everyone obsessed over the first variable, engine torque, but Frank realized the multiplication factors were equally important. More importantly, he discovered that keeping the engine in its optimal torque band through precise gear selection was worth more than raw horsepower that only appeared at high RPM. Let me put this in perspective. A 446-pack Chrysler made peak torque of 490 lb-ft at 3,200 RPM. Impressive, right? But with a 2.76.1 rear gear and a wide ratio transmission, it spent most of its acceleration time outside that peak torquey band. Meanwhile, Frank's 396 made 415 lb-ft at 3,200 RPM, 75 lb-ft less. But with different gearing, it could stay within 500 RPM of peak torque all the way to 80 miles per hour. The result? More average torque to the wheels despite less peak torque at the crank. So, what was Frank's weird trick? It was actually 3 modifications working in harmony, and none of them were what you'd expect. First, he didn't port the heads for maximum flow. Instead, he reduced the port volume by welding in material and reshaping the short side radius. This increased velocity at low and mid-range RPM. The heads actually flowed less at peak lift, 235 CFM versus the stock 248 CFM, but below 0.400 ride lift, where the valve spent 80% of its time, they flowed 15% more. Second, he modified the intake manifold using a technique he learned from studying aircraft engine design. He created what he called wedges velocity stacks, inside the manifold. These were carefully shaped aluminum tubes that extended from the plenum into each runner. They looked bizarre, like someone had stuffed trumpet bells into the intake. But they eliminated the turbulence at the plenum to runner transition and increased air velocity by 22%. The engine couldn't breathe as well at 6,000 RPM anymore, but from idle to 5,000 RPM, it was transformative. The third modification was the most controversial. Frank changed the transmission gear ratios. Not the whole transmission, just the gears. He had a machine shop cut custom gears with ratios of 2.541, 1.811, 136.1, and 1.1. Compare that to stock, 2.521, 1.881, 1.46.1, and 1.1. Tiny changes, right? But combined with a 390.1 rear gear instead of the stock 3.311, these ratios kept the engine between 3,000 and 4,200 RPM during acceleration to 80 miles per hour, right in the meat of the torque curve. The first time Frank took the modified Chevelle to Milan Dragway, nobody paid attention. It looked stock except for wider rear tires and traction bars. No hood scoop, no screaming graphics. The primer spots from where Frank had welded in frame connectors made it look like a work in progress. Then he ran a 12.91 at 108 miles per hour. For context, a stock L34 Chevelle typically ran mid-14s at about 98 miles per hour. Magazine test cars with the L78 375 horse motor were running low, 13s at 105.9 but here's where things got weird. Frank's trap speed of 108 was actually lower than some L78 cars that ran slower, ETs. A car and driver test L78 had trapped a 110 but ran a 13.2 ET. How was Frank's car quicker with a lower trap speed? Because trap speed measures velocity at the finish line. ET measures how quickly you covered the distance. Frank's modifications meant his Chevelle accelerated harder where it mattered, the first 1,000 feet. By the time other cars were finally getting into their power band, Frank was already approaching the finish line. The street racing community in Detroit was brutal. Reputations were made and destroyed in seconds. Word spread quickly about the primer-spotted Chevelle that was hunting big blocks. A guy with a 1970 Plymouth GTX with the 440 Super Commando called Frank out at a Gratiot Avenue cruise night, 440 cubic inches, 375 horsepower, torque flight automatic. On paper, it should have been close. From a 30-mile-per-hour roll, Frank put 3 car lengths on him by 80. The Plymouth owner accused Frank of running nitrous. Frank popped the hood. No bottle, no lines, no solenoids. Just that weird-looking intake manifold with the internal velocity stacks. And then came the magazines. Hot Rod heard about Frank's Chevelle through their network of Detroit correspondents. They were skeptical. Every month someone claimed to have found the secret to free horsepower. Usually it was BS. But their tech editor, Roger Huntington, was intrigued by the velocity stack concept. He'd seen similar designs in aircraft and motorcycle engines, but never in a car. In November 1971, they brought Frank and his Chevelle to Union Grove Raceway in Wisconsin for a full test. Andy and the Hot Rod team came prepared with their own test equipment. They wanted to verify Frank's claims scientifically. First, they baselined a stock L34 Chevelle SS. It ran 14.42 at 98 miles per hour. Then, Frank made his passes. First run, 1288 at 107. Second run, 1291 at 108. Third run, 1286 at 107. The consistency was remarkable, but the Hot Rod team was confused. They'd tested a 454 LS6 Chevelle earlier that day. 454 cubic inches, 450 advertised horsepower. It had run 12.72 at 112 miles per hour. Quicker, yes, but only by a tenth and a half, despite 100 more rated horsepower. They put Frank's car on their portable dynamometer. This is where things got really interesting. Peak horsepower at the wheels, 271. The LS6 had made 342 wheel horsepower. Frank was down 71 horsepower at the wheels, yet his car was nearly as quick. The answer was in the torque curve. Frank's engine made 310 lb-ft at the wheels at 3,200 RPM and stayed above 290 lb-ft all the way to 4,800 RPM. The LS6 made 365 peak, but only in a narrow window around 3,600 RPM. By 4,400 RPM, it had fallen to 280 lb-ft. Don Dan and Roger Huntington spent 2 hours going over Frank's modifications with a photographer documenting everything. The velocity stacks fascinated him. Frank explained his theory. Everyone's trying to move the maximum amount of air. I'm trying to move the optimal amount of air at the highest velocity. It's not about peak flow, it's about average flow velocity throughout the entire intake stroke. Frank had essentially created a tuned length intake system, something that wouldn't become common in production cars for another 20 years. And the head modifications were equally clever. By reducing port volume, Frank had increased port velocity from 195 feet per second to 247 feet per second at 3,500 RPM. This created better fuel atomization and cylinder filling at street RPMs. The smaller ports actually hurt high RPM performance. At 6,000 RPM, the stock heads would have made more power, but Frank's engine never saw 6,000 RPM. It didn't need to. And Hot Rod published their test in the February 1972 issue with the headline, "Cass the Torque Multiplier, How a 350-horse 396 Runs with the Big Dogs." The article caused a sensation. Frank started getting calls from all over the country. Racers wanted to buy his velocity stacks. Engineers from GM's Tonawanda engine plant wanted to examine his modifications. A representative from Edelbrock offered him $50,000 for the rights to produce his intake manifold design. Frank turned them all down. He wasn't interested in fame or fortune. He just wanted to go fast. But the real validation came from an unexpected source. Chevrolet was developing the next generation small block, which would eventually become the LT1. Engineers were struggling with emissions requirements that were killing performance. One engineer, Thomas Langdon, had read the Hot Rod article and convinced his superiors to let him study Frank's Chevelle. In March 1972, Frank drove to the GM Technical Center in Warren, Michigan. For 3 days, GM's engineers tested every aspect of his car, and what they found challenged conventional thinking. Detroit had been in a horsepower war for so long that they'd forgotten about efficiency. Frank's modifications improved brake-specific fuel consumption by 18% at part throttle. His velocity stacks reduced pumping losses. His gear ratios kept the engine in its most efficient operating range. In an era when gas was starting to become expensive and emissions regulations were tightening, Frank had unknowingly developed solutions to problems Detroit was just beginning to face. The GM engineers were particularly impressed with Frank's approach to gear ratio selection. He'd used calculus to optimize the ratios for minimum time to distance, not maximum speed. He showed them his notebooks filled with integration equations, calculating the area under the acceleration curve for different ratio combinations. One engineer later said, "Reese, we had computers doing this kind of analysis." Frank did it with a slide rule and graph paper. Think about that for a second. A tool and die maker working in his garage had out-engineered entire departments at General Motors, not through luck or accident, but through methodical analysis and creative problem-solving. He'd treated his Chevelle as a system, not just a collection of parts. Every modification was designed to work with every other modification. The result was greater than the sum of its parts. The street racing scene in Detroit changed after Frank's success. Suddenly, everyone was talking about torque curves and gear multiplication. The old formula of Larn bigger engine equals faster car Z was being questioned. Frank had proved that intelligent modification could beat brute force. His Chevelle became legendary, not for what it had, but for how it used what it had. Then there's a particular night that old-timers still talk about, Telegraph Road, summer of 1972. A guy showed up from Chicago with a 1970 Dodge Challenger RT with a 446-pack, fresh build, headers, slicks, the works. He'd heard about Frank's Chevelle and drove 4 hours to race it. They lined up at a light near Eureka Road. When they launched, Frank got the jump. His lower first gear and traction advantage put him half a car ahead immediately. The Dodge started pulling in second gear. Its horsepower advantage was showing. But when Frank grabbed third, his closer gear spacing meant less RPM drop. The engine stayed in its power band. The Dodge fell behind and never recovered. Final margin, 2.5 car lengths. Then the Dodge owner was furious. He demanded to see under Frank's hood, convinced he was running nitrous or hiding a bigger engine. Frank obliged. The crowd gathered around as he explained his modifications, the velocity stacks, the port work, the gear ratios. Some got it immediately. Others remained skeptical. How could weird-looking tubes in an intake manifold make that much difference? But the stopwatch didn't lie. Frank's Chevelle was running elapsed times that shouldn't have been possible with its power level. And then by 1973, the party was over for muscle cars. Insurance rates were astronomical. Gas prices had doubled. Emissions regulations had neutered engines. The L34-396 was discontinued. The horsepower wars ended not with a bang, but with a whimper of low compression, smog-controlled motors that made less power than engines from 10 years earlier. Frank's Chevelle became even more of an anomaly, a reminder of what was possible when engineering trumped brute force. Tedant, Frank kept racing and refining the Chevelle until 1975. His final setup was even more radical. He'd developed a ram air system that used computed fluid dynamics principles he'd learned from aerospace journals. The hood looked stock, but underneath was a complex network of sealed ducts that created a high-pressure zone at the carburetor inlet. At 60 miles per hour, it was worth 8 horsepower. Not much, but combined with his other modifications, it was enough to run consistent 12.7s at 109 miles per hour. The last recorded race was against 1971 Plymouth Cuda 440+6 at Milan Dragway in October 1975. The Plymouth was heavily modified, aluminum heads, roller cam, 4.56 gears. Its owner claimed 500 horsepower. Frank's Chevelle still had the same basic 396 short block he'd built in 1971. 4 years of racing on the same bottom end. The Plymouth got the better launch, pulling half a car by the 60-foot mark. But Frank's setup started working its magic in second gear. By half-track, they were even. At the finish line, Frank was ahead by half a car length. 1271 at 109 versus 1284 at 114. Lower trap speed, quicker ET. The Frank Moretti special. And then what happened to Frank and his Chevelle? In 1976, he took a job with Ford's Advanced Engineering Department. The skills he'd developed in his garage were exactly what Detroit needed as it struggled with fuel economy and emissions requirements. His Chevelle went into storage in his garage, covered and preserved. He'd occasionally start it, let it warm up, remember the old days. But he never raced it again. The moment had passed. None of the Chevelle survived, though. In 2018, Frank's son donated it to the GM Heritage Center. It sits there now, still wearing its primer spots, still running the velocity stack intake, still geared with Frank's custom ratios. GM engineers occasionally study it, marveling at the sophistication hidden beneath its rough exterior. The velocity stack principle Frank pioneered? It's now standard in many modern engines, refined with computational fluid dynamics, but based on the same concept Frank developed with tin snips and a welder. There's a lesson in Frank Moretti's story that goes beyond cars and racing. It's about the power of systematic thinking. Frank didn't have the biggest budget or the most powerful engine. He had curiosity, determination, and a willingness to question conventional wisdom. He proved that understanding the principles behind performance was more valuable than simply throwing money at horsepower. In an era of excess, he achieved more with less. Tendritchna in modern automotive engineering has validated many of Frank's insights. Variable valve timing keeps engines in their optimal operating range. Direct injection provides the precise fuel control Frank was trying to achieve with his velocity stacks. Dual-clutch transmissions maintain power delivery between gear changes. 8, 9, even 10-speed automatics keep engines in their power band. Every one of these technologies is trying to solve the same problem Frank tackled in his garage: how to extract maximum performance from available torque. The muscle car era is remembered for its excesses. The huge engines, the wild graphics, the astronomical horsepower claims. But Frank Moretti's Chevelle tells a different story. It's the story of American ingenuity expressed not through excess, but through efficiency. Not through corporate resources, but through individual determination. Not through conventional thinking, but through creative problem-solving. When enthusiasts gather at car shows, they gravitate toward the Hemis, the Copos, the Boss 429s. The rare, the powerful, the expensive. But those who know the history, who understand what really matters in performance, they look for different things. They look for the details that suggest someone understood the science, not just the catalog. They look for the modifications that required thinking, not just spending. They look for cars like Frank's Chevelle. Tena Onanen Frank Moretti passed away in 2019 at the age of 82. At his funeral, dozens of Detroit racers from the old days showed up. They told stories about racing Frank, about learning from him, about how he'd changed their understanding of performance. His son spoke about finding notebooks in the attic filled with calculations and theories Frank never had the chance to test. Ideas about aerodynamics, about suspension geometry, about weight transfer. The mind that had revolutionized street racing with velocity stacks had never stopped questioning, never stopped learning. Nintin. The automotive world has changed dramatically since Frank's heyday. Modern cars make power levels that would have seemed impossible in 1969. A new Corvette makes 670 horsepower from 376 cubic inches. But the principles Frank discovered remain valid. Torque multiplication still matters. Keeping an engine in its power band still matters. Efficiency still matters. In fact, in an era of turbocharged four cylinders making 300 horsepower, Frank's ideas matter more than ever. There's something beautifully American about Frank's story. A working man with a high school education out-engineering college-trained professionals. A backyard garage producing innovations that corporate R&D departments missed. A David versus Goliath tale where David wins not through divine intervention, but through applied mathematics and creative thinking. It's the promise of America distilled into metal and math, that with enough determination and intelligence, anyone can compete with anyone. And today, when someone claims they've found a weird trick just to make power, we're usually skeptical, and rightfully so. The internet is full of snake oil and false promises, but Frank Moretti's weird trick was real. It was based on physics, validated by testing, proven in competition. It showed that sometimes the weird tricks are actually fundamental principles that everyone else overlooked. Sometimes the backyard mechanic really does know something the engineers don't. So, the next time you're at a car show or a drag strip and you see a car that seems to run quicker than it should, ask questions. Look closer. There might be a Frank Moretti behind it, someone who approached performance as a problem to be solved rather than a product to be purchased. Someone who understood that in racing, as in life, it's not about what you have, it's about how you use it. What's the most impressive sleeper car you've ever seen? The one that shocked everyone when it ran? Drop a comment below and share your story. Because the spirit of Frank Moretti lives on in every garage where someone's trying to go faster with science instead of just cubic inches. And if you enjoyed this deep dive into one of muscle car history's most fascinating stories, hit that subscribe button. We've got more tales of automotive ingenuity coming your way.